Welcome back. This is part 2 of my Introduction to Definite Integrals series. And in this one I would like to discuss how integrals can be used to find areas under curves. Now areas and integrals are different, but integrals can still be used to find out the areas. So there are 3 basic steps to finding the area using integrals. The first one, here are the steps. Oh, this is not writing. Steps. So the first one is to partition the interval that the integral is found on, so a to b, in using the zeros. So using the zeros of the function, you can partition everything and just make note of where the zeros are. And then you should integrate over these new subintervals. So wherever you found the zeros, you're gonna. So if you have something that goes from 5 to 15, and you have zeros on 6, 10, and 13, then you can just you have to integrate first from 5 to 6, then from 6 to 10, then from 10 to 13, and then from 13 to 15. So you have to integrate on all these separate subintervals. So then you have to integrate over these new subintervals. So that's what that means. And then the third step is to add all these together. So you're going to get some negative values, but you're going to make them positive because the areas are always positive. You can't have negative areas. So add these positive values together. So those are the 3 basic steps. So let's try an example. So let's say you have y is equal to 3x minus x squared over the main interval of 0 to 4. So the graph of this looks something like, so if you're going from 0 to 4, here's 0, goes like that, and then just goes down. So this is 0, 1, 2, 3, 4. And this whole area is, this is the area we're looking for. So from 0 to 3, and then 3 to 4. So first we want to make note of the zeros. So obviously we have a 0 at 3, and you can even see this if you can do 3x. If you don't want to graph it, graphing is one way of doing it, but you can do 3x minus x squared is equal to 0 and just factor out the x and find where the zeros are. So x equals 0 and x equals 3. If you solve this, you can see there are 2 zeros at 0 and 3, and the factoring method proves the same thing. So anyways, so we've done the first part. We partitioned the thing using zeros. Now we have to integrate this over the subintervals. So you want to take the integral first of from 0 to 3 of 3x minus x squared. That's in 3x minus x squared. And then you want to integrate from 3 to 4 of 3x minus x squared. And this value, of course, is going to be negative, but we're going to ignore the negative, and then we'll add the 2 of these together. So now that we have a clear idea of what we're doing, let's actually do this. So the integral of this is 3 over 2 x squared minus 1/3 x cubed. These are just the antiderivatives, and you can see if you integrate 1/3 x cubed, you'll get x squared, and same here, you'll get 3x. And that from 0 to 3. Right. And you get, let's see, if you plug this in here, you get 27 over 2 minus 9. Let's plug that, yeah. and that equals 4 1/2. And the next one, again, you do the same thing. Same antiderivative function, but this time we're going from 3 to 4. And when you plug values in here, you get, let's see, 16, 8, 20, 24 minus 64 over 3 minus, because now you're subtracting, because this is, again, if we remind ourselves, integrals are at the antiderivative, and you're subtracting these two values in this case. Oops. This is b and that's a. This is b and that's a. So then, if you do that here, then you're subtracting the other part, and you get 27 over 2 minus 9. Because it's just the same thing here again, and the reason we didn't, the second part here was 0, so we could just ignore the rest, because both of these values would yield 0. And then, anyways, when you subtract, going back to this one, you subtract this from that, simplify it down, you get 2 2/3 minus 4 1/2, and you get negative 11 over 6. But as we said before, these are areas, so we want to ignore the negative sign. The only reason the negative is here is because we did an integral. So 4 1/2 plus 11 over 6 is equal to 6 1/3, and that is the total area of this.